So, what if the key to acing your next coding interview has less to do with raw talent or just grinding endless problems and more to do with having a genuinely smarter plan? We're going to explore exactly that: how to build a precise, algorithm driven roadmap that gets rid of the guesswork and replaces it with a system that actually works.
Think about your current study plan for a second. Does it feel a little chaotic? Maybe you're jumping from topic to topic, hoping some of it sticks, but you don't really have a clear sense of direction. If you're just picking problems based on what feels right, you're probably working hard for sure, but maybe not smart.
In this kind of chaos is what I like to call the interview prep maze. It's a super common trap. You've got all this enthusiasm and you're putting in the effort, but it just doesn't seem to translate into success. Without a solid plan, it is incredibly easy to get lost, frustrated, and just totally burn out.
And hey, see if any of these sound familiar. You're trying to learn something like trees before you've really mastered arrays. That's like building a house without a foundation, right? It just leads to total confusion. Or maybe you've spent weeks on really hard problems only to realize you've forgotten the basics of Big O. And the big one, without planning time to review, the stuff you learned last month just vanishes. It goes to show it's not about how many problems you solve, it's about how you build up that knowledge. So, how do we fix this? Well, the solution is to start treating our study plan like it's a computer science problem itself. We're going to build what I call an algorithmic blueprint, a system that organizes our learning in the most efficient way possible, just like we design an algorithm for a coding challenge. First things first, we need a data structure. Let's define something called a topic. Just think of concepts like arrays, graphs, or dynamic programming as these little individual objects, and each one has a few key properties: how much time it'll probably take to learn, a priority score, and, most importantly, a list of its prerequisites.
Okay, once we have our topics defined, we can actually model the entire curriculum as what's called a directed acyclic graph, or a DAG for short. This is the core idea right here. Every topic is a dot, a node, and an arrow from one to another means it's a prerequisite. And it's acyclic because you can't have a crazy loop where topic A needs topic B, but topic B also needs topic A. That just wouldn't make sense.
Let's actually build this out visually. We have to start with a topic that has zero prerequisites, a true foundation, like Big O and complexity analysis. On our graph, this is a node that has no arrows pointing to it. It's a genuine starting point.
All right, next up, let's add another topic: arrays. Now, to really analyze array operations properly, you absolutely have to understand complexity. So that means arrays has a dependency on Big O. And so we draw a directed arrow from Big O to arrays. And this isn't just a line on a diagram, it's a rule. It literally enforces that you have to master the parent node, Big O, before you can even think about tackling the child node, arrays. This simple structure is what stops you from accidentally learning things in the wrong order. Okay, so we've got our graph model. It's this big, beautiful map of knowledge. But a graph isn't a weekly schedule, is it? We need an engine. We need something to process this graph and turn it into an actual step-by-step plan. And that engine is a very specific and very powerful algorithm.
And that amazing algorithm is called a topological sort. Its whole reason for existing is to take a complex web of dependencies, like our DAG, and just flatten it into a single ordered list. The final output is a perfect sequence where, for every single dependency, the prerequisite always comes before the topic that needs it. No exceptions.
So how does it actually work? Well, a really common way is using something called Kahn's algorithm. You start by finding all the topics that have no prerequisites. Those are the ones that are ready to go. You pick the one with the highest priority and you learn it. Once you've completed it, you can imagine all its arrows pointing outwards just disappear, and that unlocks new topics that are now ready to be learned. You just keep repeating that process, always picking the highest priority available topic until your entire graph has been turned into a perfectly ordered study plan. And this brings us to a really critical misconception. So many people think, I'll just pick an order that feels right to me. The source material is crystal clear on this. That is false. Violating prerequisites doesn't just slow you down, it creates these huge gaps in your understanding that force you to go back and relearn things later. An algorithmic approach just avoids that whole mess. So we've modeled the problem, we've run the algorithm. What do we actually get out of it? Well, you get a concrete, week-by-week schedule that's tailored to your available time. This is where all that theory becomes real-world practice.
So take a look at this sample schedule. Week 1, we're covering the basics, Big O and arrays. But here's the really clever part. Look at week 2. It doesn't just jump to the next thing. First, it schedules a short review for Big O to make sure that knowledge sticks. Then it introduces new topics like hash tables and binary search, which were unlocked by what we did in week 1. See, it's an intelligent, dynamic schedule.
Now, for all of you who are curious about the nitty-gritty computer science here, the algorithm that spits out this plan is incredibly efficient. We're talking a time complexity of O of V plus E plus W log V, where V is your topics, E is the prerequisites, and W is the number of weeks.
Okay, so what on earth does all that technical jargon actually mean for you? It means this whole process is ridiculously fast. For any normal study plan, generating your optimal, personalized roadmap for the next 3, 4, even 6 months happens almost instantly. It's efficient from beginning to end.
Let's talk a bit more about those review sessions because, honestly, they're the secret weapon here. The system automatically bakes in spaced repetition. So after you learn a topic, it'll pop in a little review session a week later, and then maybe another one 3 weeks later. These short reviews take just a tiny fraction of the original study time, but they are scientifically proven to skyrocket your long-term memory. So the stuff you learn in week 1 is actually still fresh in your mind come week 12. All right, let's bring this all together. What is the ultimate payoff here? Why is this algorithmic approach so much better than just hopping on a website and grinding random problems?
Well, when you put them side by side, the difference is just night and day. An algorithmic plan is aware of all the prerequisites. Random practice is totally unordered. Our plan puts fundamentals first, while random practice usually just sorts by easy or hard, which is not the same thing. And with spaced review built right in, your retention is systematic, not just based on hoping you remember. It's the difference between an optimal learning path and a high-risk gamble that's full of gaps.
So if you're going to remember anything, remember these 4 steps. First, model your learning as a graph. Second, use a topological sort to get the right learning sequence. Third, allocate your time each week based on topic priorities. And finally, and this is crucial, schedule those spaced reviews to make sure that knowledge actually sticks around.
So I'll just leave you with this one question to think about. You're putting in the hours, you're putting in the hard work to prepare for these interviews. But is your plan working just as hard and just as intelligently as you are? Because with the right algorithm, it absolutely can.